This lecture is going to be about Anova. This is a technique developed by Sir Ronald Fisher, and I've heard estimates that Anova has been used roughly about 3 million times. So if he was to be cited for each Anova, he would be one of the most cited authors of all time. Anova is used when we have more than two group or categorical predictors. Okay. And continuous response. You'll often see Anova graphically where the response variable is continuous here and your X predictors are set up on here. So you would have your X predictor here. The assumptions of Anova. One, that you have I, D. And if you remember what this means, it means no temporal or spatial autocorrelation. What that means is that all your points are independent of each other. One violation of this, in fact, a commonly used method is repeated measures Anova, where a response, continuous response is measured in a group over time. Second assumption. So your points are random. And lastly, that the errors are normal. Okay. And if we look at so take three groups, and let's say these are our observations for group A, B, C. And just grab one of these, blow it up. There's the mean. What errors being normal is, if we look at the distribution of these errors, so remember that errors are observations that don't match the mean. So whatever's driving this response, there's something different than what is driving the overall mean. So there's something in addition to the mean. If we were to take a histogram of these responses, what we should get is that they are normally distributed. And we can check that after we do the experiment and figure out what the means are. Okay, very broadly speaking, Anova could be used for hypothesis testing. When we use it for hypothesis testing, the null hypothesis is that the groups are equal, and we express that as saying me1, me2, and me3, etc., up to k groups. The null hypothesis is that all the means are the same. The alternative hypothesis is that any group does not equal some other group. Okay. So if we express this graphically, what the null hypothesis is saying, if we had one mean for the entire experiment, and we'll call that X bar is the entire average, and we had three groups, say groups A, B, and C, our data would be symmetric about that overall mean. And the alternative to this, the way you reject the null hypothesis, is that at least one group is different from the other. So A could be different than B and C, or we could have B higher or lower than the other groups, or all three groups could be different from each other. So one of the strengths of hypothesis testing is it's very simple. You know if your treatment has an effect, but one of the great drawbacks of hypothesis testing is when you reject the null, you don't know which group is actually different. All you know is that at least one of your groups is different. And we'll get into in the future how you tell which group has a bigger effect. So one approach to Anova is hypothesis testing. The other thing you could use it for is modeling. Okay. In a modeling approach, what you're interested in is a particular model where your observations are yi, put those there, and you want to know what the effect is of being in a particular group. So we have a beta is how we quantify effects, J is how we indicate the group, and we always have our error. So this alpha here is equivalent to X bar. And a way to think about a modeling effect is, let's go where we actually have an effect. Let's put in our overall mean. The way you want to do this is you want to parameterize the effect of, or what beta is, when X is A, okay? Here, epsilon is the errors. So any Y is a function of the overall mean plus the effect of being in a particular group, and then errors. So you don't always equal the mean of that particular group. Okay, how do we do our analysis of variance? So the big thing to keep in mind is that analysis of variance means we're going to take an experiment with variance and partition it into the variation that can be accounted for by our treatment and the variation that is due to error. So let's just make up an experiment. We'll have groups. Let's just say we're looking at a drug. We have levels low, medium, and high. And this is some physiological response. We can look at, let's just say, metabolism. So we can look at oxygen uptake per minute. And let's say this drug hypothetically increases metabolic rate. So we expect a dose response So we'll generate some data, imaginary data. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Let's add another one here. 1, 2, 3, 4, 5. And let's add another data point here. So here we have an experiment with 5 replicates. So we're going to say little n equals 5 and big N equals 15. So we have 15 total, and that's broken down into 3 groups. This notation here, little n and big N, that's my notation, okay? This is not any sort of standard notation. In fact, many publications will often ignore the number of replicates and just give you the total sample size, which can be a little bit misleading depending on the number of groups. Okay, the way to think about how we're going to analyze this experiment. These data produce a cloud. This cloud of data looks like this. And we want to know how much of this cloud of data is due to the difference in the means of each group and how much is due to the error, which is this spread. Let's put in the means of each group. Again, I'm not calculating this. It's just a guess where they might be. Okay. So to partition this, first we need to define the variance, okay? And the way we define the variance is we need our sums of squares total. And that'll be to define this entire cloud. And the way to do that is we take the sum, okay, of each observation. So I represents individual observations, okay? And we'll get to it, but J will represent which group we're in. So that'll indicate which group we're in. We take each observation and we're going to subtract the grand mean, okay? And we'll square that, right? So we examine this difference, we square it and add it up for all observations, okay? The grand mean would be the mean for, if we were to add up all the observations and divide by 15. Okay, that gives us the grand mean. So we have group means and the overall mean. Okay. To get our variance, we take our sums of squares and we divide it by the degrees of freedom. So our degrees of freedom, okay, since we're looking at all these observations, would be, we're going to use big N minus 1, okay? We call the variance in Anova mean squares. So the way to get that is we're going to take our sums of squares total, which I'm just going to call SS sub t, and we're going to divide that by n minus 1. All right. We also need, so that defines our cloud, right? And now we need to define 2 other parts. That which is due to difference in means and that which is due to error. Okay, to get the variance of the treatment, we're going to call that SS tau. Okay, So tau is gonna just a symbol that represents how much is the sums of squares that's due to the difference in things. That is equal to, we're gonna sum, okay, the difference between each group's mean and the overall mean. Okay, we're going to take these distances and square them up. So if you remember, the way we indicate group is with a subscript j. And we're taking the mean and subtracting the overall mean. Okay, we want to square that up. For degrees of freedom, okay, we also need to count for the sample. So we're going to put in a small n sub j. So for each group, we look at the mean, we're going to multiply by the number of observations within that group. The degrees of freedom are k minus 1, which is number of groups minus 1. Okay, so to get mean square treatment, we take sums of squares, tau, divided by k minus 1. Now, the interesting thing is, if we look at the mean square total, okay, that is going to be the sum of the treatment plus the mean square of the error. And we could just simply add these, or excuse me, you could actually subtract the treatment from the total to get the error, but it's always good to calculate it as a double check. So let's do sums of squares error, and that's going to be equal to sum of the squares of the difference between, okay, each observation accounting for the group. So we're only going to look at the within group minus the mean. So we're going to take each observation within this group and subtract it from the mean and square it. Add that to the difference between the squared distances for this group, and add that to the squared distances of all these observations minus this mean. The mean square error is going to be equal to the sums of square error over the degrees of freedom. Degrees of freedom now are going to be k little n minus 1. So little n is the number of replicates. This is the number of groups minus 1. So k n minus 1. I'm sorry, that is incorrect. It's actually number of replicates minus the number of groups, n minus k. Okay, so in this case, we have 3 groups. So it'd be, we have 6 replicates, 3 groups, so it would be 6 minus 3. Okay. Now that we have our mean square treatment and our mean square error, we can look at the ratio of these two. Let's think about what this means. This is what I consider to be the signal. Okay, so this is the part, if we ignore error, This is the variance that's due to the treatment. So this is how the differences in means drive this cloud. Mean square error, I think of as noise. And if we take any one of these, the noise is the observations that don't fit the mean, okay? So we can look at the signal to noise ratio and determine if we have a significant effect. And we call this ratio the F, okay? So F equals the signal to noise ratio, or the mean square treatment over the mean square error. And this F test is when we determine if it's significant or not. The F distribution is a continuous distribution, so this ratio is going to be continuous and depends on the degrees of freedom, but typically it looks something like this. Okay, so it's skewed right, and we have one about here. 0 goes on, our continuous distribution goes on and on. And this F distribution is generated from the null hypothesis. So think about what this might mean. If the null is true, right, then our signal should be small compared to our error. And these things should be about 1, okay? And if we look at the distribution, that's what we are. So our F's, the way to think about this is, so if we have 1, 2, 2.5, 3. So the way to think about this is, if we have 2, okay, that means there's about twice as much variance due to the treatment than there is noise. So for any degrees of freedom, this shape will be slightly different. But what we're interested in is this area of the curve that represents 0.05. So that's the probability of getting the critical value or more extreme, okay, given the null is true. So if we look at the F distribution, if we're using an alpha 0.05, we're looking at that area of the curve that has a 5% probability or more extreme occurring if the null were true. And we test the F, okay, with a particular alpha and 2 degrees of freedom. So if you look up an F table on the internet, you'll find that there's 2 degrees of freedom. One is your degrees of freedom for the treatment, and the other is degrees of freedom for the error. So in our example, if you remember, we're going to say 0.05, because that's pretty standard. We had degrees of freedom treatment. We had 3 groups, so we have 2 degrees of freedom for our treatment. And our error, right, was, it's n minus k. So we had 6 replicates minus 3 groups, so that would be 3. Okay, so we look at the F distribution with this error rate and 2, 3 degrees of freedom. Okay. Okay, so what we're going to do now is just talk about what you need to report after you did an Anova, and just an Anova. One of the things you might want to report is your R squared. And R squared is a measure of how much of your model of the Anova is accounting for the total variance in the model. And a way to think about it is if you look at the sums of squares over the treatment over the sums of squares total, gives you a rough idea of what the R squared is. R squared can go from 0, theoretically, to 1. But what you'll find is, even if you fit a random data and did an Anova, you'll never get 0. So don't ever expect to see 0. 1 means that the treatment effects account for 100% of your variation, but that's equally unlikely. So let's just say if you get near 1, that's better, and if you get near 0, that's worse. So just to give you some scenarios. So if your data looks something like this, or you have some error and not too much, you might expect an R squared of, let's just say 0.8. You can also get the same thing if you have smaller effects and then tighter data. Okay. So R squared can be a bit misleading in that it's taking into account the total cloud and your effect size. So if you have, since it's this ratio, if you have a smaller cloud, smaller effect size can also give you large R squareds. Okay, so just be cognizant of that. And again, when you see an R squared, also look at the graph and compare these two things. Okay. Okay. What to report? Usually in the method or the results section, you're going to write something like this. Sorry, you'll actually want to state what the degrees of freedom are. So it might look something like this, for example, where this alpha would be 0.05. We have 4 groups and then 25 replicates. And you say that equals, and then some number, comma. This is your sample size. Normally you would do things like report degrees of freedom right here, but it's already reported here. Or you could, on the other hand, write this as this. So 0.05 equals some number, and you could say DF treatment equals whatever, making up numbers here, degrees of freedom, error equals 22, and you'll always want to throw in your exact p-value unless it's absurd. And what I mean by absurd, let's say you have a p-value of 0.01 or 0.12. An absurd would be if you had a p equal to 0.00001. You could report that, or you could just say p less than 0.001, for example. You're going to want to state in your results whether you reject or fail to reject. Okay. And you want to report any outliers, what you did with outliers, and always graph. Now your graphs, okay, box plots are going to be best. Okay, so your box plot should look something like this. R generates a nice box plot. Okay, so your graph should look something like this. Okay, you want to label each group, right? A, B, and C, and you'll want to label your y-axis and always have the units. So like, let's say blood pressure in millimeters per milligram, for example, if that's how it's measured. Okay, and then the other thing is, I like this. You don't see it much anymore, but I like to see the number of replicates with little n's, for example. And by placing these replicates along with the box plot, you can see how well this box plot is characterizing data. So in N is 7, you know that this box plot might change given more data. And N of 22, you can be relatively confident that this is what your data actually looks like. Okay, for this lecture, this part of the lecture, what I'm going to talk about are the alternatives to one-way Anova, the parametric where we assume that the errors are normal. The non-parametric version to test for group differences is the Kruskal-Wallis. The Kruskal-Wallis test. Okay. What that test does, you can imagine an experiment with 3 groups. What that test does is first it assigns ranks to all the observations, independent of group membership. Okay, so here are the ranks. It's not perfect, but it doesn't need to be. And what it does is it compares the ranks, the distribution of ranks according to groups. And what you would expect is if one group is different, again, the null for the Kruskal-Wallis is that the ranks, okay, the ranks of any group is these ranks are not equal. So so what it will do is it will add up the ranks and compare the sums of these ranks And you can imagine if there was no effect, these ranks would be much more balanced. So these have many more smaller ranks, and these have the higher ranks, the larger numbers. And if we have some experiment with no effect of the group difference, the rankings would be much more equitable across here. Okay, so there wouldn't be any large differences. And that's what it looks for, is any one group that that's different from the other two groups. So these two are pretty close, but if this stands out and has many more higher numbers, you may end up rejecting this hypothesis here. So what you want to report, first you'll always want to report in a methods which test to use, and then why. And the why is because you have continuous data, but the errors were not normal. So what that would look like is if you had, for example, some data with some real but noticeable outliers. So you end up with skewed data. Okay, so skewed data is very appropriate for the Kruskal-Wallis test. The statistic is an H. So you would want to report what your H value is, your degrees of freedom, and the p-value. Okay. So again, you always want to justify why you use a particular test, and then the result should be a presentation of the actual test statistic, degrees of freedom, the p-value, and of course, we always graph it. And a graph appropriate for Kruskal-Wallis is, again, a box plot. Okay. And what's nice about the box plot is if we were to box plot these data, it might look something like this. Okay. Where it actually, you get to see skewedness of the data. Okay. Now, that's just one alternative. So we use Anova and Kruskal-Wallis when we have continuous data. And we're interested in mean differences. So that's our test. And the predictor, of course, is groups. But what if this is not continuous? What if we have counts? So what if we have a count? And for example, we might have hospitals A, B, and C, and we're interested in the number of patients coming in and visiting that hospital. Anova would not necessarily be appropriate in this case, and this could be an average over, say, a week, number of people coming in per day. So we have a number of tools available to us where we could actually look at this and use Poisson. I use a Poisson distribution. We could also have binary data and also have groups. So we could have patients that are recovering from a disease or not. And we could have groups. So this could be, again, hospitals. And then we would use a form of logistic regression. Okay, that accounts for groups and does not have to be continuous in either one of these cases. Okay, and that concludes the lecture on Anova.